Okay, Brian Miller-Hicks here, continuing my series of PowerPoints in engineering geology. Now I'm going to talk about a very important, crucial step in an engineering geologist's scheduled services, and that is conducting and executing site investigations. Site investigations are undertaken and completed to determine subsurface conditions, characteristics of soil, bedrock, groundwater, which may affect construction of a project, give us ways to characterize the soil and bedrock in order to possibly mitigate or improve foundation conditions, such as removal and replacement with compacted fill, or to excavate stiff plastic clays, or to determine shallow groundwater and take steps to mitigate that condition. So, as I said, it's a critical step in services that an engineering geologist will offer. So, what are the stages of a site investigation? Well, they're fairly, should be self-evident to a good engineering geologist. They can be varied for more limited investigations or expanded for more complex investigations. First thing we do when we have gotten information on the location of the project and the type of project is we do a desk study. Look at aerial photos, look at topo and geologic maps, anything, any mapping that's available, city maps, fault maps, maps showing landslides, and especially significant and helpful can be previous reports on properties adjacent to the project property that you're working on. So we use that preliminary study, looking at photos and maps and reports, to develop a pre-investigation ground model of what we might expect, what we might anticipate. Okay? Then we go out into the field. First try at the project site is to do reconnaissance mapping. So we look for faults, fractures, bedding. If we found any in the desk study, we got to look for those things where exposure is available. Then we can go ahead and plan the ground investigation. Are permits required? In San Diego County, you need boring permits for any borings that are deeper than 20 feet or will encounter groundwater. Look at access. Can we get a drill rig in there? Can we get a backhoe in there? Do we have to demolish something? Do we have to open gates? We got to look at if we're drilling on or near roadways. We've got to get traffic control plans, permissions from city for right-of-way access. Very importantly, very significantly, we need to know where any underground utilities are. Water lines, storm drains, electric, gas pipes, etc. So with all that done, we can figure out, well, what kind of equipment can we get in there? Can we get a drill rig, truck-mounted drill rig in there? Can we get a backhoe in there? Can we get a portable tripod type rig that can be carried in by a few men? Can we dig manual hand pits? Will that give us our information? Okay. Then we actually do the ground investigation. We go out with a site plan and with all this pre-acquired knowledge of the site and do our borings, our pits, our trenches, geophysical surveys if those are warranted, on sites where we possibly may have deep, loose alluvium, groundwater. We might do cone penetrometers where, let's say for example, in the LA Valley areas, alluvium is very deep, very thick, so we may want to go 100 plus feet with our probes, which lends itself to an investigation using cone penetrometers. I'll get you more detail on that kind of exploration equipment later. Okay, so we're going to drill, dig, we're going to get samples, we're going to do mapping. Once that's done, 1 day, 2 days, 3 days, a week, whatever it may take, we get the samples and we take them back to the laboratory to do laboratory tests. Sieve analysis for texture, direct shear for strength, natural density and moisture. Is it very wet? Is it very dry? Expansion properties, especially for plastic clays. If they get wet, they can expand and compromise foundations and utilities, roadways, etc. Consolidation, are these underlying sediments so soft that if you put a load on them, they may sink? So that's something to look for. Okay, we get all this information, all this data, we put it together in a report, an investigation report. That's going to contain our findings, our conclusions, our recommendations, with appropriate data, maps, and graphics, a complete characterization, geotechnically speaking, geologically speaking, of the subject site and how it will affect the construction of the project, or how the construction of the project may affect the site. It goes both ways sometimes. So, look here, site investigation is critical. I've had some clients in the past that try to cheap out, try to cut corners on a site investigation, not realizing that $5,000, $10,000, $20,000 spent on a site investigation are well worth the dollar cost for a project that's going to cost them $2 million, $3 million, $4 million. If a site investigation is done incompletely, not thoroughly, and something is missed, that may well result in increased site preparation and construction costs, which you don't want to stick your client with. So you try to do as complete an investigation as possible. Okay, so the objectives of a site investigation, I've probably touched on them just now. What is the suitability of the particular site to the project that's being planned? Is it suitable? Sometimes a site will have soil rock conditions that are so cost prohibitive that it's not worth it. Let's say you want to build a small one-family residence, but find that it's situated on a huge landslide where you might have to excavate 40, 50 feet to dig out the loose material and restabilize the hillside. That's cost prohibitive for one small house, so that may not work. The next objective would be design. The site investigation lends itself to the preparation of a well-executed design. Is it adequate design for site conditions? Is it economically feasible for site conditions? Then the next objective is to give recommendations for construction. Best methods, look for material sources. Let's say you're going to excavate a bunch of soil out of the site, so you need a source to bring in soil and perhaps build up fill. Let's say it's a really rocky site, so you want to get rid of the real hard rocky material and bring in nice, smooth, easy to work with silty sand, for example. Disposal areas, let's say it's full of junk, old fill, full of garbage, full of nasty organic materials. You want to take all that stuff out and put it somewhere. Well, you have to figure out where you're going to put it. Effects of changes to the site. What if the site is subjected to intense rain, if it's on a hillside? What if it's subject to earthquakes because it's very close to a major fault system? The impact of the project on environmental conditions, the impact of the project on neighborhoods, the stability of adjacent structures that have been there for a while, for example. So sometimes you'll go through a whole investigation, a list of things, and you might have to tell the client, look, this site's not going to work. Let's look for another site. And that does happen fairly rarely in my experience, but it can happen. Okay, so let's look at that geologic model that I talked about that's going to be formulated pre-investigation. What is the project? You have to have a really good, thorough understanding of the project. Is it going to be a bridge? Is it going to be a hospital? Is it going to be a high-rise? Each of these types of projects have different parameters you need to look for. Skyscraper in a downtown area, for example, might be included in the design an underground parking garage. So you have to know what excavation conditions are. You have to know where groundwater is. You have to know if there's any earthquake faults underlying the site. For a hospital, hospitals are very sensitive structures that are controlled by State Department of Architects in California, and they're subject to quite stringent and demanding seismic parameter analysis, for example. For a bridge, of course, obviously, you want to know that the foundation conditions for the pylons and for the bridge abutments, for the bridge columns is stable, so that has to be thoroughly investigated as well. So understanding of the project obviously is critical. So generally speaking, your investigation guidelines will include the mapping out the selection of locations for borings and trenches, etc. For the depth of investigation, rule of thumb that's found in some textbook is 1.5 times width of foundation. In practical terms, though, that's not always observed. So if you have a 50-foot wide building, you don't generally go 75 feet. In San Diego County, it's often adequate to go till you hit nice, dense, firm formation. Where you put the borings and trenches sometimes will be controlled by the client specifications. I've done some projects on Coronado at the old Miramar air traffic, the old Miramar Air Station. So the military has very rigid and precise guidelines for investigations, sometimes unreasonably so, if I may say so. And of course, ASTM guidelines are very useful in planning and executing investigations. So once we do the kind of the reconnaissance work and a very preliminary desk study, the engineering geologists and geotechnical engineers will put together a proposal for the client to review and either accept or reject. It has to include an understanding of the project, the scope of work for the investigation, how long it's going to take and how soon it can be started, the cost of the investigation, a discussion, generally speaking, of geologic issues. You don't want to get too detailed before you actually explore the site, but you may have some knowledge preliminary to the investigation of faulting, landslides, etc. It should include the type of exploration equipment you're going to use. Should have a plan for sampling, the depths at which samples are obtained and the types of samples which will be obtained, a lab testing program, preliminary lab testing program, and then a discussion of the report and what it's going to contain. So here we are at a point where we can conduct a field investigation. First step is reconnaissance. Got to go out and look at the site. What does it look like? Well, let's look at this thing. This is in the Spring Valley area of San Diego County. This doesn't look too good. What is all this stuff? This is all dumped fill. So you may not have seen that in aerial photos. It may not be on any maps, but it's important to note before you get started. You may want to tell the client that, look, we're going to have to handle this old fill, get rid of it, or reuse it, filter out the bricks and concrete blocks, etc. Okay. Exposures. You want to look at exposures. This happens to be an exposure which is hard to see here, but I believe there is a fault running through here. This is in San Diego County. So obviously, as geologists, we're trained to look at exposures that show geologic conditions on vertical and horizontal scales. Utilities, I mentioned that. It's important to note where utilities are. The worst thing you can do in an investigation, or one of the bad things you can do, is to actually penetrate a gas line or water line or sewer or storm drain with your drill rig or your backhoe. That can be a mess. It can be a costly mess and something to avoid if possible, whenever possible. So in California, we have a state agency that takes care of some of the locations for us. Contact 811 on your phone. They will come out to the site after you've pre-marked it, put stakes or paint where you might be digging or drilling, and they will let you know whether there are any utilities that are known by the state or the city and where they're located. Sometimes this isn't enough. On private property, the state agencies won't go into private property to locate utilities. So in those cases, it's incumbent upon the investigator to hire a private utility location service to go in with utility locating equipment onto the site and look for any buried pipelines or utilities. So that's to cover yourself in two ways. Sorry. So exploration and sampling methods is next. What do? We use backhoes. In this case, we're looking for possible faults in the San Diego area. Got this property owner wanted to build an ADU, additional dwelling unit. So we go in with a backhoe to dig a trench. Here it is here, and look for any exposures or indications or evidence of fault traces on the trench walls. These trench walls have to be carefully logged and scraped clean, and the stratigraphy has to be mapped out and logged and presented in a report. Limited space investigation. Sometimes it's necessary to crawl under an existing structure, like my friend is doing here. He's looking at the condition of the existing foundation, seeing if there's any problems with moisture, etc. So sometimes it's necessary to do that. And in my experiences, the young and the fit people can get in there and do that work for me. Here's a picture of some various types of drill rigs that are used in site investigations. Truck-mounted auger, both of these can go fairly deep, 50, 60 plus feet. This is what I mentioned before, where equipment can be ported or carried into a backyard site. This is what's called a tripod rig. Limited access, you can't get a truck back here. So you get this rig in, and they can drill typically with a 4-inch diameter auger, limited depth, limited power, so they're not suitable for every kind of site, but they can certainly do an adequate job for some sites. We have another limited access type rig, which is set up on a steep hillside, and you'll note there are crawler tracks on this rig, so that it was able to get access this hillside and set up and do some drilling. Here's a couple more. Here's another limited access hillside track mounted drill rig using an auger. Tracks are noted here. Pretty powerful, and they can go fairly deep. But the thing with these limited access rigs, whether it's tripod or track mounted, is they take more time than a regular truck mounted rig, and typically they're somewhat more expensive than a truck mounted rig. Finally, this picture of a bucket auger. Bucket augers have been used in Southern California for decades. I don't know how long. I was using them back in the 80s, 1980s. And they're typically used for landslide investigations, where this, instead of an auger, you have a bucket which drills down, fills up with soil, then the bucket is pulled up and the soil is dumped. That leaves you with a big, wide diameter hole, 24 inches to 30 inches in diameter, that you can actually lower a geologist down that hole in a steel cage, hopefully, and look for any features of landslides such as slide planes, distorted bedding, and that kind of thing. It's, I'll tell you, I've been down a lot of these types of holes. The deepest hole I went down was 118 feet. It's not for the faint of heart. It's something you have to be careful with. You have to lower gas meters down to make sure there's no toxic gases in the hole. And you don't want to obviously go down below groundwater, because you can't log anything while you're underwater. And in some landslides, typically, or sometimes, right at the contact between landslide deposits up above and solid stable ground down below, you usually have groundwater sitting on top of that plane at that depth. Here's another type of drilling I was involved with a few years ago. NASCO, which is a shipbuilding consortium on San Diego Bay, had one of their dry dock facilities break down and fail. So this is the dry dock that's now flooded with water. So they wanted to rebuild the dry dock, which meant we had to take a drill rig, truck-mounted drill rig, put it on a barge. This is the barge you see here, pretty old barge. And then we lowered the auger through the water into the bottom of the bay, and we went another 95, 100 feet, I think, with our drilling to see the nature of the unconsolidated bay bottom sediments, try to reach firm formation and get that depth so that they knew how to design their new dry dock facility. So it's an unusual type of drilling. You don't do it every day. I was lucky enough to be involved with this one. Remember when I mentioned the bucket augers for landslide drilling? Well, here's a situation where there's no way to get the bucket auger rig into the backyard of this existing house other than lifting it over the house using a large crane. Kind of risky, yeah, but we did it. We managed to do it. Cost a lot of money, but it was to look for critical information on the structure and location of the landslide plain in this area near San Diego. Here's a depiction of the type of rigging that's used to lower a geologist into a bucket auger hole. Safety harness around the geologist, an air hose, a gas detector, voice-activated intercom, rock shield at the top so that any falling rock can bounce off harmlessly. If you're down 50 feet and a 3-inch pebble finds its way onto your hard hat, you're going to feel that, you're going to hear that, and it's not a pleasant feeling, believe me. So this is a geologist being lowered into that hole. Again, not for the faint of heart, but you can derive a lot of very valuable information by looking at structure and depth of the landslide plain and the disturbed material versus the undisturbed material. Standard penetration tests, so I'm talking about sampling here. Just to, let's see, what does this show? This shows conventional type of sampling with a split barrel steel tube. Here are the specifications for outer diameter, inner diameter. Here is the anvil, and here is the hammer. So 63.5 kilograms is roughly 140 pounds, 30-inch drop. Every time you raise the hammer and drop it. You're supposed to drop it 30 inches onto the sampler. When you do that, you count the number of blows of the hammer it takes to penetrate 1 foot, say every 6 inches. So 10 blows per 6 inches, 20 blows per 6 inches. It gives you an idea of the relative density of the material. The denser the material, of course, the more blows it's going to take to drive into the material. Here is what's called the California split spoon sampler. It's got a 2-inch inner diameter, 2.5-inch outer diameter. It's a steel tube, pretty strong, with a shoe. Here's the cutting shoe. So that's the bottom end that's driven into the soil. It's got a sharp edge on it. The interior, in the interior of the tube, you see these steel tubes, which are lined up like so. But more usefully, we use brass rings of 1 inch in thickness for the bottom 6 inches of the sampler, so that when we retrieve the sampler, we have 6 brass rings filled with soil, hopefully, that can then be individually used to run various tests like direct shear, density, moisture, etc. This is the standard penetration test sampler, which is more narrow in diameter, 2-inch outer diameter, 1.5-inch inner diameter. And with this, the advantage is it's a bit quicker, loading and unloading the sampler, and you get a better idea of the stratification of the material you're driving through. Because it's narrower in diameter, it takes less blows to penetrate 1 foot than it does to penetrate the California split spoon sampler, which has a wider diameter. So here are some handy tables that we use to get relative density. So in silts and clays, very soft, we get 2 blows per foot. That's very soft material. A very hard clay, we would get 32 plus blows per foot. That's with a standard penetration sampler. For sands and gravels, if you get only 4 blows in the material, that's loose, very loose. If you get 50 plus blows, then it's very dense. So here's one of my boring logs as a sample. Excuse me. This is a field trench log. Yes, it's not a boring, it's a trench. And so you write a material description in here. Here are indications of the sampling. And so we had 4.5 feet of fill. And then we had 4.5 to, 3.5 feet of alluvium or fill, not quite sure. And then more alluvium, and the bottom at 9 feet. So this is generally what a field trench log or boring log would look like. Let's talk about rock coring. These rock cores were extracted during a landslide investigation for a school in San Diego County. We went down, as you can see, at least 95 feet. So in order to core rock, you need a special kind of drill rig that can core through rock. Diamond bits, using a lot of water and high-speed rotation. So this is what the core looks like when it's extracted, and it's important to keep in mind the sequence of the sampling. So this is the shallower sample, then the next deeper, and next deeper, and the next deeper, and then the deepest. I mentioned cone penetration testing is useful for deep alluvial sites, or sites with perhaps thin layers of alternating sands and clays. These kinds of borings give you some detailed pictures of subsurface conditions. Here's photos of what these cone penetrometer rigs look like. Here's a truck mounted one. Here's a more remote, limited access one. And here again is one mounted on tracks. Cone penetration test rigs. Here's how they work. So they've got a cone at the bottom, as you may have guessed, for adequate and strong penetration. They're used in soft, loose, or liquefiable sediments, liquefaction assessments, which of course are important when judging the vulnerability of a project site to liquefaction during a seismic event. During large earthquakes, if you have saturated loose sands, those sands can liquefy and settle and can cause settling or sinking of surface layers, which isn't good for buildings, bridges, and other structures. This is what the logs look like. I won't go into a lot of detail here, but they give you a real detailed look by cone resistance, friction ratio, pore pressure where water is involved, shear wave velocity. So you get a lot of data from these cone penetrometer rigs and their borings. So they're often used in deep alluvial areas that are prone to earthquakes and vulnerable to liquefaction. So we're talking mainly about soils, and I'll talk a little bit about hard rock investigation. Hard rock investigation obviously involves material of much denser quality. We often use seismic or geophysical methods to determine relative density of bedrock and conduct rippability studies. So rippability studies are used to determine whether you can rip a rock mass with a bulldozer or whether you have to blast it with dynamite or some other explosives. So using a fairly simple method of a hammer and a plate and a line of geophones, the geologist strikes the plate with a hammer, which sends energy that's picked up by these geophones and transmitted to a seismometer, which will record the depth and velocity of the waves and give you a subsurface profile. So it will give you a picture of P waves, which are primary waves generated by that energy, sort of a simulation of earthquake P waves. Some other types of surveys, they use shear waves, which are slower, of course, but which are more likely to be near surface waves generated by earthquakes. Again, the hammer energy is a simulation of earthquake energy that's used to determine subsurface rock profile. So what do? Seismic refraction surveys allow us to map bedrock topography. Why? We can determine the depth of gravel. We can determine the depths at which layers change, let's say from gravel to sand or gravel to clay. We can pick up water tables sometimes with geophysical surveys, the depth of the water table. In areas like Florida or other karst topography areas, we can detect subsurface caverns and voids. I've mentioned rippability, the relative density of rock and whether it can be ripped by heavy equipment or dynamite blasting. Sometimes we can pick up faults and fractures by looking at detailed structural profiles. We can look for large boulders, and we can monitor different changes in elastic properties, which give us more clues of rock properties. So here's a picture of the seismic refraction method. Here's the energy source. The hammer on the plate sends energy down, which then travels along the contact and back up to a geophone detector. So we can build a profile which shows us unsaturated, drier soil sitting on top of water-saturated soil, and it gives us the P wave velocity of 1,000 foot per second on the top layer, 5,000 on the middle layer, and 15,000 feet per second in the bedrock. So it's very useful to give us subsurface profiles and gives us relative density via the P wave velocity of each layer. Let's see. So here's a geophone array. Velocity 1 is 5,000 feet per second. Velocity 2, 10,000 feet per second. So this shows, as you might typically expect, is that surface or near surface materials have lower velocities, therefore they're less dense than the deeper, higher velocity materials. So this is a useful chart. The yellow color is rippable material, means you can rip it with a dozer, D8, D9, whatever. Marginal is the gray, and then non-rippable is the black zone. So anything that's above this velocity, this is meters per second, feet per second. So anything above 7,000 feet per second is in the blast zone, more or less. And each different rock type has slightly different regimes of velocity, and where some is more rippable than others at certain velocities. For example, shale is still marginally rippable up to 8,000 foot per second. But if you look at igneous rocks like granite, it's perhaps a little bit denser than the shale. So it gives you relative velocities and the relative properties of different types of rock. So here's a different type of graphic representation called tomography. Difficult ripping, probable blasting, easy ripping near the surface. This is what's called a hydrotrack drill. A hydrotrack drill is used instead of seismic refraction surveys. We use hydrotrack drills, which are air percussion driven type drills with a hammer and hydraulics and air pressure that hammer into the rock at repeated hammer blows, and the rate of penetration, in other words, number of feet per second penetrated by this air-driven rock hammer, gives us a relative density profile. So drill penetration rate at seconds per foot. If it can go 1 foot in 20 seconds or less, it's rippable. If it takes more than 30 seconds per foot, then it's non-rippable, or blasting is likely. So here's some drilling rate chart, seconds per foot. You can see here this rock got up to 60 seconds per foot. I don't know what it is, probably some kind of volcanic rock. So at this depth, from 20 feet to 32 feet or so, you pretty much get into a blast zone. And then up above, this is still rippable. And below that, it gets a little bit softer. So it gives you a pretty accurate profile, which can be invaluable when you're doing the large and deep excavations for construction